So we're going to find tangent lines and tangent planes using the gradient vector. So a property of the gradient, so kind of remember what the gradient is, the derivative of f ds is in the direction of u at p naught. We define this to be the directional derivative of f at that point. And we know that this is done by just the gradient vector at p naught dotted the u vector. So we'll just, get away the points and kind of say that df ds is just the directional derivative of f, in the direction of u. And we know that this is going to be the gradient dot u. So there's a property of dot products that u dot v is equal to the magnitude of u times the magnitude of v times the cosine of theta, which is the angle between. So really what I'm trying to find is, when does this become a maximum? Well, since this dot product can be written as the magnitude of the first vector times the magnitude of the second vector and the cosine of the angle between these things. And this thing will be a maximum. Now, since the cosine function is bounded between -1 and +1, this is going to be the biggest when the cosine is equal to 1. So that means that this directional derivative will increase the most when the cosine of theta is equal to 1 or when theta is equal to 0. So we can see that the magnitude of a unit vector is just 1, so this is going to be the gradient of f times the cosine of theta. Now, since the cosine of theta is just going to be 1 at angle 0, this is just going to be the magnitude of the gradient. So really what this comes down to is, how do we find where this thing increases the most? Well, at this particular point here, if I map it up to this curve, if I find the gradient and then evaluate it at that point, it is going to be, where it increases the most. So where it goes, we'll just say kind of uphill the most. So I can see that it looks like from my picture that it's increasing the most rapidly here. And that thing happens to just be the gradient of f evaluated at p naught. So here's our example. I want to be able to find the tangent line of, say, this function. So consider the function x squared over 4 plus y squared is equal to 2 at the point -2 comma 1. So I've drawn the ellipse, I've drawn the point, and what I'm trying to do is I'm trying to find the equation of that blue tangent line. Now we're going to use gradients to be able to do this, and the claim is that this function here is some level curve of a three-dimensional, I keep saying blanket curve, but so our solution is that if I have a function x comma y, which is equal to x squared over 4 plus y squared, then this equation is a level curve. Then x squared over 4 plus y squared equals 2 is nothing more than just f of x comma y is equal to a constant. So that's why it's considered a level curve. Basically, if we think about the xy plane being the domain, I'm asking, when is the z value always equal to 2? So if we were able to graph this function here, and I'll try my level best. Let me pause it and do that. So here's the best image I have of this thing. And really what I can see is that this is, quadratic in both, the x and y direction. So it looks a lot like a satellite dish, except it's, a little bit squished. So this will also be squished in one of its coordinate directions. And I've drawn the same pink curve, which is going to be the level surface. I should have did it a little bit better, but this level surface right here is where, when this, this paraboloid or the satellite dish is, z equals 2. And what we know about a property of the gradient is that it increases the most in the direction of the gradient at that particular point. So if I'm going to choose that point, let's see, x is 2 and y is 1, so somewhere about right here, x is 2 and x is -2, x is -2, y is 1, so we're actually talking about that point. And then this blue curve that goes around here. If I was going to find its gradient vector, well, its gradient vector is going to go, where it increases the most, so it kind of looks like this. So its gradient vector is going to look like so. Now, what we'll actually notice about this is this gradient vector, if I look top down on it, it would look just like this. That's what its gradient vector would be. And what we notice is that this vector is going to be normal to that curve. And we know something about, well, we practiced a little bit of tangent lines and also tangent planes, but we know from a tangent plane, let's kind of remember this, So remember, so if I have a tangent plane, x is equal to x minus, so a times x minus x naught, b times y minus y naught, plus c times z minus z naught is equal to 0. This is the equation of a tangent plane that has normal that is going to be, you know, ai plus bj plus ck. Now, if I want to do a tangent line as opposed to a tangent plane, so let's say, remember the tangent line, if let's do it that way, the tangent line, well, that means I don't need all three dimensions, so get rid of this z, so this will be equal to 0. And here, get rid of this part of it as well. So this will have that normal. And notice that since a and b are the normal, a and b is really going to be, you know, the direction of this, which really is going to be your gradient. So this normal is going to be, you know, df dx evaluated at that point, p naught I plus df dy evaluated at that point, j. So really, these pieces here are nothing more, your a and b are nothing more than your partial derivatives. So your partial derivatives of this function, of the left-hand part of that function. So if I want to find df dx at this point, well, I have to find the partial derivative of this. So the partial derivative of this is going to be, you know, 2x over 4, so this would be x over 2. So let's do it this way. This is going to be equal to x over 2, evaluate at the point minus 2, 1. I know it's only got an x coordinate, but that's okay. Sometimes partial derivatives will have both. And then the derivative with respect to y is just going to be 2y, you know, evaluated at minus 2 comma 1, you know, j. So plugging this in, this is minus 2 over 2, so this would just be minus 1i, and plugging this in is going to be plus 2j. So really this is just going to be your, this really is going to be your a, and this is going to be your b. So our tangent plane is going to be minus 1 times x minus the point, which is going to be minus that negative 2, plus b, which is going to be 2 times y minus its coordinate is going to be negative 1 or minus 1. So then simplifying this, this is going to be negative 1 times x plus 2 plus 2 times y minus 1 is equal to 0. So this is the tangent line in implicit form. Of course, we can solve this thing for y and then see if it at least makes sense to us. So minus x minus 2 is going to be 2y minus 2 is equal to 0. So not plus. So 2y is going to be equal to, we have minus x, put that to the side, minus 2 minus 2 and minus 4, so the other side is going to be plus 4. So then divided by 2, y is going to be equal to 1/2 x plus 2. So that would be its dependent, or its explicit form. And looking at that this really does look like that it has a slope of 1/2, and it looks like it's got a y-intercept of 2. Now I want to do another example to where I want to find the derivative of, the equation of its tangent line, but I'm going to give an explicit form of the equation, and then just kind of show you how this, this piece here simplifies a little bit if it's an explicit form. All right, so here's our example. I want to find the tangent line to this function, y is equal to x squared minus 5x plus 1, at the point 2 comma minus 5, and I just kind of verified that when you plug in 2 that this does spit out minus 5. So this point is a part of that function, is a solution point. So in order to do this, I need it to be a level curve of a function that has two independent variables, x and y. So what you do is you just leave the constants on the right-hand side and you put all the variables to the left. So if I redo this, this is going to be negative x squared plus 5x plus y is going to be equal to 1. And it's kind of your choice. You can do it this way. You can, if you don't like this to be positive, you can send it to the other side. This would be negative. This would be negative. This would be negative. So let's do that because it tends to have a derivative of negative 1. So we'll send everything to the other side. Say negative 1 is going to be equal to x squared minus 5x minus y. So it's kind of our choice. So really this is going to be our curve. So really it says that our f of xy is going to be equal to negative 1. And whatever this thing looks like graphically, I don't need to graph it. I know the geometry of why this works. Okay, so in order to find this, what we know is that we're going to need the gradient evaluated at this point of this function so I can find the normals a and b to this line. So let's find that. So df dx evaluated at 2 minus 5 is going to be, well, the derivative with respect to x is going to be 2x minus 5, and that'll be 0. So I'm going to evaluate this at 2 minus 5. So 2 times 2 minus 5, so this is going to be equal to negative 1. Now, we also have to do df dy evaluated at 2 minus 5. Now, what we'll notice is, since this was an explicit equation solved for y, that means you could have isolated y all by itself. So the derivatives of these pieces will just be 0 with respect to y. The derivative of this with respect to y is just going to be negative 1 regardless of the point. So this is going to be, negative 1 evaluated at that point, which is still just going to be negative 1. So now when we create our tangent line, it's a times x minus x naught plus b times y minus y naught is equal to 0. What we know is that your a and b are simply these two coefficients. It's funny we got negative 1 twice, but it is what it is. So, a comes from the derivative of f with respect to x, evaluated at x minus this 2, and then plus b, which is going to be this one, which is going to be negative 1 as well. What's interesting, again, this is kind of the big point of this, is if this is done explicitly, this thing will always be negative 1, assuming you send all your variables to the right and all your constants to the left. Times y minus minus 5 is equal to 0. So then we can simplify and do this explicitly. So minus x plus 2 is equal to, I keep doing that, minus y minus 5 is equal to 0. So let's send everything over. So minus y is going to be equal to x. This is negative 3, so the other side is going to be positive 3. So y is going to be equal to negative x minus 3. Okay, so the real beauty of mathematics is, or it's really, I can consider it superpower, is it can extend into multiple dimensions. So what we can do with a tangent line, we can kind of extend this into 3 dimensions and do the exact same thing with a tangent plane. So let me show you an example of that, and then we'll find a tangent plane to a particular blanket function at a particular point. So we're going to find the equation of the tangent plane to this blanket function at this particular point. So what we know is that this looks like some function that's going to live over really the point x equals 1 comma 2, and then it's going to map up to 4 on that function. So I'm not going to draw its. I know it's quadratic. I guess you really could. It does look like, it does look like this essentially. But it's going to be shifted down 9 units, so really your x and y axis are going to come out through here. So what I'm trying to do is I want to find the equation of its tangent plane at that particular point. So instead of a tangent line, these now have tangent planes. So if I want to find this at x equals 1, y equals 2, so x is 1, y is 2, down 4, it's going to be about right here. And what you'll see is it looks like some kind of plane that is going to be tangent to this, a paraboloid at that particular point. So we're going to be able to find that. So very similar, what's going to happen here is we know the equation of a tangent line is going to be equal to this. Where a, b, and c are nothing more than the partial derivatives of this particular function. Now, when I do this particular function, I'm going to have to, this is equal to z. So this is the same thing as z equals. So when we send this to the other side and I can send the constants to the left, I know that this can be written as x squared plus y squared minus z is equal to 9. which really says that this is some level surface of some x, y, z function that's equal to 9. And since it's some level surface, I know that the partial derivative of this thing is going to be normal to this plane. So that has the exact same concept that we did with tangent lines. So I'm going to have to find its derivative. So what is df dx evaluated at the point 1, 2, minus 4? What is df dy evaluated at the point 1, 2, minus 4? And then your df dz evaluated at 1, minus 2, minus 4. Well, I already know that's pretty easy because this was an explicit function. So when you send this to the other side, it's just going to be equal to -1, similar to the other example. Now, if it's not explicitly solved, sometimes they write it in an implicit form. This thing will actually have a partial derivative. So the derivative of this with respect to x is just going to be 2x evaluated at 1, -2, so 1, 2, -4. So just plug it in 1. This is going to be 2. The derivative of this is going to be 2y evaluated at 1, 2, minus 4. So plug in y. This will be equal to 4, and this will be equal to -1. So finally, your tangent plane is going to be equal to, these are the coefficients, 2 times x minus, well, the point's going to be at 1, plus 4 times y minus 2, plus, plus a -1, so -1 times z minus a -4, so plus 4 is equal to 0. And then, of course, we can simplify this, 2x minus 2 plus 4y minus 8 minus z minus 4 is equal to 0. So a lot of times with planes, they like to just keep your linear combination of x, y's, and z's on the left-hand side. And then they'll throw your constants to the right-hand side. So -2 minus 8 is a -10, so -14. Put it on the other side is 14. So that is that in a nutshell. So we have tangent lines and tangent planes using the property of gradients.